We call them eyes in the sky, these silent observers circling our planet, giving us this incredible God's eye view of everything, from our busy cities to the deepest, most remote forests. Today, we're going to pull back the curtain on the amazing tech that makes this all possible and reveals secrets that are, well, hidden in plain sight.
So think about this for a second. How do you actually see through the swirling clouds of a hurricane to map the floodwaters below? Or how do you spot one tiny little fire starting in a forest that's thousands of acres wide? I mean, these aren't just thought experiments, these are real-world problems. And the answer is a technology called remote sensing, which is really just a way of seeing the unseen and measuring our world in some absolutely astonishing ways.
At the very heart of this technology is the sensor. And here's the best way to think about it. Everything on Earth, everything, the soil, water, buildings, plants, they all interact with energy in their own unique way. Some things reflect sunlight, others soak it up. Some things give off a lot of heat, others not so much. A sensor is basically built to pick up on all those tiny little differences and turn them into data that, we can actually understand and analyze.
Okay, so if you're building one of these eyes in the sky, the very first, most fundamental choice you have to make is this. Are you just going to listen for the light that's already out there, from the sun? Or are you going to bring your own flashlight? This right here is the core difference between what we call passive and active sensors.
It's actually pretty simple when you break it down. A passive sensor is a lot like your standard camera. It needs a light source that's already there, usually the sun, to see anything. And that means, of course, it's not so great at night, and it definitely can't see through clouds. An active sensor, on the other hand, is like a camera with a flash. It blasts out its own pulse of energy. Think of radar or LiDAR, and then it just measures what bounces back. And that is its superpower. Because it controls the light, it can see day or night, rain or shine, and often right through the clouds.
All right, so we figured out if the sensor has a flash or not. The next big question is, well, how many colors can it see? And I'm not just talking about red, green, and blue like our eyes. We're talking about a sensor's power to see across the whole electromagnetic spectrum. We call this its spectral resolution.
So the most basic type is called a panchromatic sensor. The easiest way to think about this is like it's taking a super sharp, high-definition black and white photo. It basically grabs all the visible light and puts it into one channel. Now what do you lose? Well, you lose all the color. But what you gain is incredible detail. It's absolutely perfect for when you need to see the crisp, sharp edges of things like buildings or roads. Next up, we've got the real workhorse of remote sensing, the multispectral sensor. This is the one you'll find on most satellites, like the famous Landsat series. It sees in a handful of different color bands, the usual red, green, and blue, but, and this is so important, it also sees in bands our eyes can't, like near infrared. And why does that matter? Because healthy plants reflect infrared light like crazy. This sensor gives us that perfect sweet spot between seeing detail and being able to tell the difference between a field, a forest, and a river.
And then there's the superhero, the hyperspectral sensor. Forget a few color bands. This thing sees in hundreds of super narrow, continuous bands. It doesn't just see green, it sees hundreds of different, distinct shades of green. This gives it the power to create a unique spectral fingerprint for almost any material on Earth. We're talking about not just seeing a forest, but telling you what specific kind of trees are in that forest, or finding a specific mineral deposit from orbit. The catch? As you can imagine, it creates an absolutely staggering amount of data.
So, in a perfect world, a sensor would have that super color vision, be able to see a ladybug from space, be ultra-sensitive to the tiniest changes, and revisit every single spot on Earth every minute of the day. But that's just not possible. The reality is that designing a sensor is a game of trade-offs. It's a balancing act. The best way to think about it is like building a character in a video game. You can't max out all your stats. And these character stats are called the 4 resolutions. You've got spatial resolution, which is all about clarity. You've got spectral, which is the color vision we just talked about. Then there's radiometric, which is all about subtlety. And finally, temporal resolution, which is about frequency, how often it looks at the same place. Let's quickly break them down.
First up is spatial resolution. Just think of this as the zoom level. How small of an object can it actually see? A sensor with a 1-meter resolution means each pixel in the image covers a 1 by 1 meter square on the ground. That's detailed enough to easily spot a car. A low-resolution sensor, on the other hand, might have 1 kilometer pixels. You can't see the car, but you can see the entire city in a single shot.
Second is spectral resolution. And we just covered this one, right? It's the sensor's color vision. Are we talking about the simple black and white view of a panchromatic sensor?
the few key colors of a multispectral sensor, or that incredible supercolor vision of a hyperspectral sensor that can basically taste the chemical makeup of what it's looking at.
Third, we have radiometric resolution. This one sounds complicated, but it's really about sensitivity to brightness. How many shades of gray can it see between pure black and pure white? A low-res sensor might only see a few, but a high-res one can see thousands. That lets it pick up on incredibly subtle things like tiny changes in how moist soil is or how murky the water is in a lake.
And last but not least, temporal resolution. This one's easy. It's the revisit rate. How often does the satellite pass back over the exact same spot? High temporal resolution is crucial for tracking things that change fast, like a wildfire or a flood. You might get a new picture every single day. Low temporal resolution might mean you only get an update every couple of weeks.
And this brings us to the single most important rule in all of remote sensing. You can't have it all. It's all about the trade-offs. If you boost one of these stats, you almost always have to sacrifice another. That satellite that can see your car from space, it probably has a really narrow field of view, which means it takes a long time to cover the whole Earth. So it's not going to give you daily updates. It's always a balancing act.
So now that we know the rules of the game, now that we know about these trade-offs, how do we actually solve those problems we talked about at the beginning? Well, it all comes down to picking the right tool, the perfect sensor for the specific job at hand.
Let's put it all together. If you're mapping a city, what do you need most? Detail. So you pick a sensor with crazy high spatial resolution. For that hurricane flood, you have to see through clouds and you need updates constantly. That's a job for an active radar sensor with high temporal resolution. Prospecting for rare minerals, you need that hyperspectral supercolor to find the unique spectral fingerprint. And if you're a farmer checking on your crops, you need to see those infrared stress signals, and you need to see them often, which means you need a multispectral sensor with high temporal resolution. See how it works?
So you see, every sensor up there is a choice. It's a carefully crafted compromise designed to answer a very specific question. And as this technology just keeps getting more and more powerful, more sensitive, and sees our world in ways we never could before, it leaves us with a pretty cool final thought. With all these new ways to see, what's the next big question we should ask our planet? What should we be looking for now?